I pluck a guitar string, I'm creating a mechanical vibration. Each string vibrates at a specific fundamental frequency. For example, the low E string vibrates at 110 Hz, meaning it completes 110 cycles per second. The pickups, which I have 3, use electromagnetic induction, which is based on Faraday's law.
There's a permanent magnet in the pickups, with coils of copper wire wrapped around it. When the string, which is made of metal, vibrates inside the magnetic field, it causes the magnetic flux through the copper to change. The changing magnetic field creates an electric current in the wire. The result is an alternating current that matches the vibration of the string. The signal is tiny, usually around 50 to 100 millivolts, and has a waveform identical to the string's motion. In both cases, electrical gain increases the amplitude of the wave, turning a 0.1 volt signal into something like 20 to 30 volts, depending on the amp and the volume settings. This is a conversion of electrical potential energy to a much stronger electrical signal capable of driving a speaker. To get maximum power transfer, the amplifier and speaker needs capable independence. Most guitar amps and cabs are rated at a 4, 8, or 16 ohms. If the impedance is too low, the amp delivers too much current and can overheat. If it's too high, the amp can't deliver enough power, resulting in low volume. Power is calculated using P equals V times I. The speaker converts electrical energy into mechanical energy using electromagnetism again. There's a voice coil attached to a cone. When alternating current from the amplifier flows through the coil, it becomes an electromagnetic. It's positioned in a fixed magnetic field, so it's pushed and pulled depending on the direction of the current. This motion pulls and pushes on the cone, which pushes and pulls the air in front of it. That movement produces longitudinal sound waves, which travel through the air to your ears. If the speaker vibrates at 110 Hz, you hear the note A. If it vibrates at 440 Hz, that's the high A. The tone controls on an amp are actually RC filters, capacitors that shape which frequencies pass through. The bass controls boosts low-frequency waves around 80 to 200 Hz. The mid-range controls affects the frequencies where the guitar's character lives, around 500 to 1500 Hz. The treble control modifies high frequencies, 2 to 6 Hz, which add brightness and clarity. By changing resistance and capacitance values in the circuit, the amp alters how strongly different frequencies are amplified. When you turn up the gain, the amplifier boosts the signal until it reaches its voltage limits. Once it pushes past that limit, the top and bottom of the waveform get clipped flat. This is called nonlinear amplification, which has introduced new frequencies, odd and even harmonics, which create the sound we know as distortion. A clean wave is smooth. A distorted wave is squared off and has more harmonic content. This changes the timbre dramatically.
So, the physics of a guitar amp look like this. 1. Mechanical vibration. 2. Electromagnetism, induction. Tiny AC signals, voltage amplifications. Speaker motion, sound waves, music. It's a full chain of energy transformations involving electricity, magnetism, circuits, resonance, and acoustics. Thanks for watching.